For this wonderful opportunity, and thank you all for being here. So today I'll talk about machine learning in cosmology. I can see some eyebrows being raised, but I want to do it in a very different way. Not in the sense of new algorithms and performance benchmarks, but rather trying to understand what machine learning tells us about how we do inference in cosmology. So the main message that I want to say is machine learning is useful, and it will become more important in the future, but machine learning shifts our perspective on how our assumptions enter the inference pipeline, and that results that is important because we need to understand better physical validation tests, not less of it. So I'll try to explain this a bit more in a general sense, and then I'll give some examples from my own work as to the message that I want to convey. Right, so cosmology is essentially an inverse problem in the sense that what we do is we start with some initial conditions and then we evolve it using nonlinear and often complicated physics, and then whatever results we have, we compare it with observations. And our goal is to do the opposite. We have these noisy, indirect observations, and we want to understand the physical realization of the truth of nature from these observations. And modern cosmology has entered an era where the data that we have has become increasingly high dimensional, not to mention that its volume has expanded. Also the models that we have made, they have become more and more expensive, and the likelihoods that we write, they are becoming increasingly complicated and also in certain cases intractable. So in this context, machine learning tools have proven quite useful in the sense that they are very useful numerical tools. You should not treat them as magic. So for example, they have been useful in speeding up expensive simulations in the form of emulators. They also help in estimating parameters in certain cases. They are used in field level reconstruction and many other applications. So it is something that people do use. But this is a quote that I kind of like because it captures the essence of the core issue that we should be careful about when talking about machine learning. And the thing is, in traditional cosmology, we encode assumptions in the form of priors, likelihoods, functions, approximations, etc. We can of course argue as to what approximations we make, but we know where those approximations lie. Machine learning, on the other hand, it does not remove those assumptions, it just relocates them behind architectures, hyperparameters, and loss functions. So the message is that you need to be very, very sure about the physical validity of the predictions that you get. So when you're using machine learning, it's not that you just throw out your physics knowledge. You have to incorporate that better to be sure that whatever your model is predicting, that makes sense physically. And I will not go into all the applications of machine learning, but I will focus on late-time reconstruction, which is one of the examples that I have worked on a bit. So here, often you have observables of this kind, like you see patterns on the sky, or you measure absolute magnitude of supernovae, or you have clustering statistics and so on and so forth. But what do we want? We want these. We want some sort of smooth functions that describe the underlying physics. For example, DL as a function of Z, or the Hubble parameter, so on and so forth. And you can do it in multiple different ways. You can use parametric methods, non-parametric methods. I'll focus more on these. And the fun here is, this is an inverse problem. So machine learning seems very, very promising, but it also makes it very risky. So I will demonstrate this with something called deep learning or neural networks, as you may have heard about this. So you don't need to understand what these do internally. What you need to understand is any deep learning architecture basically is a universal function approximator. What that means is, if you have data from some underlying distribution and you feed it into the network and it tries to learn from it, it will in principle be able to replicate that underlying distribution. That's all it does. Now we are not the first ones to use deep learning for late-time reconstruction. Many people have done this. At the time we were working on this, there were some issues like the uniqueness of the reconstruction, or even predictions of the error bars, or even underfitting and overfitting issues, which were more or less generic in the models that were in the literature at the time. So our attempt was to somewhat overcome some of these issues with ladder. So this is a code that we developed in collaboration with certain machine learning experts at my institute at ISI. And the code is publicly available. I guess a few of you have already seen this. But for those who haven't, I welcome you to have a look at that and use that in your problems if applicable. So the way ladder, the way we had posed ladder initially was we trained it using apparent magnitude data of supernovae from the Pantheon compilation. So that's the data set. So the learning problem is this. You have some noisy data and you fit a function through it, right? No, it's not that simple because Pantheon has a covariance matrix which correlates these different data sets. So that is something you need to take into account while you're training your model. So the way we do this is we take certain subsets of this data and we construct local Gaussian distributions using the covariance matrix that we have, and then sample from this distribution and then train the model. So effectively that covariance gets into the training pipeline, and then you predict not just the mean values but also its error bars. And we do this all through something called a KL divergence loss, which kind of quantifies how different your prediction distribution is from what you expect. Right, so this is the technical algorithm here. So what ladder is trying to do is it's trying to learn this underlying distribution from this sort of correlated system of apparent magnitude data. So I'm not going to go into the details of that, but I will take some time on this, which is the main thing that I want to stress upon and the main message that I wanted to start with. So neural networks or any machine learning algorithm will always give you an answer. The question is, how much do you trust that answer? So you need to be able to validate the physical viability of whatever your model says. So for example, this is just a test case where we try to impose as many physical conditions as we could without biasing the model, of course. So for example, we expect this reconstruction to be smooth. So we try to see which models or which architectures give a smooth reconstruction. We try to see which models give a monotonic reconstruction because we expect distances or apparent magnitudes to go down as distances increase. And we also check how robust our algorithm is to, let's say, noise injections in the covariance matrix and many other features. So the point is, these generic physical constraints that we have from our understanding of cosmology is important to guide these models to give better predictions. You should not blindly trust whatever they predict. Great, so we now have a code trained on some data set without assuming any cosmological model. We have validated it the best we could. I guess that's the best we could do. So what do we, oh, okay, so that's the central message that I wanted to say. These models, however you arrange them, they'll give you answers that you want, but that's the fine point. You have to understand how much physical information you give and how much you don't. Anyway, so now we have this trained model. What can we do? So we demonstrated a few different applications. So for one, the first application that we said was, well, it was trained on Pantheon, right? So assuming that ladder learned the underlying expansion history, can we ask it to predict what Pantheon plus would look like? We did that, and remarkably, although the two compilations have a bit different distribution in redshift, it was able to predict the Pantheon plus apparent magnitude quite reliably. And we tested that quantitatively by finding constraints using double CDM, lambda CDM, and stuff like that, and we found that the constraints are consistent within 1 sigma. So this tells me two things. One, ladder learned the background physics. Two, if it has learned the background physics, then it can be used as a model-independent tool to check consistency between similar data sets. So since these constraints are more or less consistent, we can say, okay, Pantheon and Pantheon plus are kind of consistent. There are certain differences, there are certain inconsistencies, those kind of show up. So that is not the point. The point is, this is a model-independent, data-driven tool to check for such inconsistencies. Yes. Yes.
So Pantheon and Pantheon plus They are completely two different way they check their system. So the pantheon class is have more supernovas included.
Sure.
Systematic also they are static better.
Absolutely.
Now you make your machine learning learn through pantheon, and then how you expect that learning can give you a completely different systematics, all those things which is pantheon class.
Yes. So we are not modeling the systematics. We are only working with the population.
But data included that, right? If you take a pantheon and covariance matrix is another and pantheon class, so those covariance matrices included the better systematic handling of the.
Yeah, I should clarify that. Thank you. Very good. I should clarify that. When we are training with the pantheon data set and its covariance. But when we are predicting at the pantheon plus redshift, we are only predicting the mean values and the errors. We are not predicting the pantheon plus covariance. So the covariance goes into training, but it doesn't really come out as a prediction output. So that is something that there are some efforts in the literature which try to predict covariance matrices, which is not a trivial thing to do. So that's a good point. Okay. The second application that I want to talk about is model independent calibration of high redshift data sets. So there are certain standard candles, if you may, which are at, so far away that you cannot really extend your local distance ladder efficiently to those redshifts. So in that sense, these observations are calibrated using the standard lambda CDM framework. But ladder provides us a way to do this in a model independent way, which is a big deal because you now have a GRB data set which doesn't have any bias towards a particular cosmological model. So we demonstrated that with a certain GRB sample, and we showed again with certain examples that the lambda CDM calibrated GRB and the ladder calibrated GRB, they are more or less consistent, but the main point is the ladder calibrated GRB is completely data driven. It doesn't depend on any cosmological model. And it gives me great pleasure because I think the greater GRB community has picked up on this, and there have been a few works as follow-up to what we have proposed. The third thing that I want to say is not just supernovae. You can use ladder trained on Pantheon or maybe any other supernova data set to use it as a tool to check for inconsistencies in some other type of data set. For example, this is a known result in the literature where we know that the angular and the transverse and the anisotropic bow are not consistent in the sense that they have some tensions in them, and this we have been able to show in a model independent way with ladder. So as you can see, like the angular bow results when subjected to early time and late time anchors, they overlap, but the 3D bow doesn't. This is a known result, but it is being shown from a data driven perspective. That's probably the third application I wanted to present. Okay, this is so the way we based on this method, what we wanted to do was, well, when you constrain some cosmological model, you usually take these three data sets, usually. And when you do that, you know that baryon-acoustic oscillations measure angles on the sky. And these can be converted to distances only if you know how big those spheres are. That information comes from the CMP by assuming some cosmological model. So from a physics standpoint, that's completely fine. That is motivated, absolutely okay. From a data scientist perspective, if you wonder, well, there's sort of a dependence of this on this. Can we decouple that? So ladder helps with that, in the sense that what we can do is we can cross-correlate this with ladder predictions. We can provide some sort of a non-cosmological astrophysical prior on distances on the absolute magnitude of supernovae and recalibrate bow. If you do that, this changes, distances from this changes, and then when you find constraints, you see that these things move in plane in this manner. Why is this important? This is important because this shift somewhat tends to alleviate both the H0 and S8 tensions. But that was not the objective to recalibrate. The objective was to decouple this dependence. This is probably a happy byproduct, but we are not. I won't stress much on this result because there are other parameters to take care of. But the new thing is the ladder gives you a way to sort of recalibrate. Wow. Okay, so that was about ladder. Okay, that was about ladder. Just to give another different example, the Hubble tensions have been talked about yesterday a lot. So in the context of GWs, this is completely different. A new sort of algorithm and a new sort of observable is what I want to discuss now. Is let's say you have GW observations which give you the distance information for events, and if through some method you have the redshifts, so you have data which has z distances and probably errors on the distances. You can use a different kind of machine learning tool, for example Gaussian processes, which again have been talked about extensively in other talks, to reconstruct the Hubble parameter. Now, this is why Gaussian processes, because here to reconstruct h of z, you need derivatives of the distance information, and Gaussian processes is very good at that. It gives you analytic derivative reconstruction in that sense. So Gaussian processes work very well, and these are some, I'll not go into the details of this, these are some results from our papers, but you notice that when you go at higher redshifts, for any mission, the errors blow up. This is a limitation of GP, because this happens because there's not much data here. There's not much data here, and this is a limitation of GP. On the other hand, ladder was able to give reliable predictions even at extrapolated regions. But this one gives you derivative information. Deep learning derivatives don't really go hand in hand yet. That is something that we're working on. So the point that I'm trying to make is, depending on your physical problem, on the physical problem that you're trying to solve, one or the other algorithm will be useful, which is something that you need to understand. And whatever algorithm you use, again, you need to be very, very careful about what validation metrics you use. For example, even in GP, like Amit was mentioning, I think somebody asked a question like, what is the dependence on the kernel? So you can, usually, if you use very similar kernels, the results don't change much. But if you use something that is completely not motivated, then your results will be very, very kernel dependent, and then you will have to question the predictions that machine learning model makes. Right, so this is the main thing I want to say. The lesson is not that whether ML is bad or not. The lesson is ML tends to shift where we place our assumptions from explicit to implicit by different architectures, loss functions, hyperparameters, etc. And that is the reason why we need to be very, very careful about validation tests and physical motivation or whatever results we get from such models. Yeah, that's mainly what I wanted to say, and I'll leave you with this slide just to tell you the other things that I'm interested in. If any of that interests you, please come and talk to me in the break, or you can write to me, and that's my website. Yeah, thank you.
Thank you.